Hello and welcome back to ZIM Explore. I'm Dr. Abstract, and in this ZIM Explore we're going to take a look at an art installation that we're going to be launching soon. Let's have a look. It's called the Shredder. Well, Sheridan Shredder. So what we're doing is it will be in a vertical monitor, so we will use this QR code, or people at the gallery will use the QR code to enter their stress that they want to shred. And then the stress will come here and it will be shredded. But because it's a vertical monitor, it will go horizontally. So let's see what the app looks like. Here's the app here. I teach at Sheridan in interactive media there, and another teacher wanted to get involved in this art exhibit that's coming up, and he thought that it would be nice if the students could shred their stresses. So that's what we're making here. To make sure that it's people in the gallery doing that, we've provided this code system here. So if I go back to the gallery, it's 640 at the moment, and there's the countdown. So 640. 640 and next, and now we can type our stress. That code system just makes it so that people anywhere in the world can't be entering stresses that will show up in the gallery. We may end up making an individual app that just lets you enter your own stress and see the stress be shredded right on your own device, and it doesn't go into the gallery, but that's another thing. Okay, let's see. Will this wind be so mighty? There's our stress, and I'll call it, well, world stress, and shred. All right, so we're going to confirm. And once we confirm, this gets sent to the shredder, which runs every 30 seconds. So we have 21 seconds until we see our shred. And that way it queues all of the other shreds as well. So those 21 seconds correspond to this little timer, which happens to coincidentally reset those numbers. But what I want to do in this Explore, though, is we'll watch the shredding. I want to show you how we did the shredding, and not necessarily all the login. So here comes the shredding. Will this wind be so mighty? And then it gets all shredded like that. Nice, huh? So then it just waits for another 30 seconds, and it will clear this. And if there are more stresses around, then it will shred the next stress. If there aren't, we'll see this fade out right here. So we want to kind of recreate that art right there. It'd be nice to actually see that one more time, just in case you missed it. Well, you can rewind the video. If you want to see it again, rewind the video. Let's go and create that shredding effect. Okay, so we'll go to the ZIM site at zimjs.com. Back in the shredder here, there's a link to the ZIM site. So ZIM is a JavaScript canvas framework, and one thing that's a little bit different about this Explorer is right on the shredder there's a how. So once the people shred it, it says how, which will lead to this Explore video. So there may be people, hopefully, seeing this video who haven't worked with ZIM before. So if you have worked with ZIM before, then bear with us, because this is for people who haven't worked with ZIM. So this is a ZIM site. People who work with ZIM know it quite well. ZIM is a JavaScript canvas framework. Right here, a JavaScript canvas framework with simple, powerful JavaScript that lets everyone from beginners to professionals code creativity. So here are some of the things that we can make. Those are connectors, they're called. So we can make connectors, we can do animations, has particle emitters. There's pens that we can draw with. It's got a frame, it's a framework. It runs animations, and these are some of the features: animation sprites, shapes, etc., components. It's designer code. It's actually made for designers who want to code. That's primarily it. It's easy enough even for kids to code, And that means it's good for everybody. So if you can make it simple enough, that's good for everybody. But we have bright colors. We're very designer friendly. I teach at Sheridan in interactive media, and we bring in a lot of designers in other fields as well and teach them how to code interactive media. We have an editor, and we'll be using the editor to demonstrate how we made the shredding. And this link right here is how you can start. So if we zoom in on that a bit, new circle, .center, .drag. That's what the code looks like, and that will make a circle that you can drag around. The 100 is its radius, and the color is there. So maybe we can try that in the editor. Here are some types of things that we can make with a JavaScript canvas framework. We can make art, games, e-learning apps. We've got lots of components. That's things like sliders and dials and buttons. And this more, we've got maybe 40 components. That's much more, many more than available in normal HTML. So in a sense, a competitor would be HTML and CSS. They make visual things, and they're great for making information sites where you have lots of text and images. But ZIM is great for making these things, data visualization, very more graphical, more shape-based, etc. So we can make interactive ads, puzzles, interactive logos, cards, etc. Any of these you can press on and come in and see that it is indeed very visual. So we're making visual things. There's interactive NFTs. This is what the ZIM pen looks like. So you can draw and make art as you draw, work with noise. So to some degree, this is called generative art, where we're making art with code. And sometimes that can get tricky, but there's a lot of things that you can do that's quite easy. You can expand this more section to see how all of these things are done, or the parts of ZIM that allow you to make art. And less, and same with if we go to another one of the things, for instance, games. People love making games, people love playing games, so why not love making games? And these are called HTML5 games made on the canvas, as opposed to console games, for instance, 3D games. So here's a game where we have to spot the odd robot, which is an evil robot amongst the good ones, and that's a mobile app. Here's one called Dazzle Fingers, where you practice making these motions, and you can charm people with them. Finger magic. Various games like Flappy Birds, but you're guiding the Cloud City through the crystal caves. Matching games, physics games. I'm going to show you a bit of physics right now as we did that emulation. Okay, so these are the types of games that we can make with ZIM. We also have ZIM, which is 2D interactivity on any 3D surface in 3D. So we can do virtual reality as well in 3D things. And that's the Texture Active Studio. We can get our apps put in stores and in apps. So we call those Zapps. And this is the Zapp store example. ZIM is, like I said, very easy. So it's coming in an average of 37%. The competitors, which are things like HTML and CSS, I mentioned, we slay there, that's for sure. But there's other ones like Flutter, which was developed by Google. P5.js is a very common one for making art, and you can see that ZIM is coming in at less than that. Phaser, Pixie, React, Angular, Vue, all that. So you can also take ZIM and put it into these other frameworks like React, Angular, and Vue. If that's the case, then you're probably one of these devs. You might want to hit the dev site and see how to do that using Node Package Manager and things that the average person wouldn't know. All right, so we're nearly through our little intro to ZIM. It's fun to code, powerful, easy to learn. Best to follow Scratch. So we actually teach ZIM to kids and school to high school. So here's a kids site, and this one right here down here are bugs, and we have a physics one as well. So bouncing bugs is physics, and we're going to show you a little bit of physics to do our emulation. But you see, it's so easy that we're even teaching these things to kids. So there's that to consider. If if you're coming in, there's a big Learn section right here. And the Learn section would be the best place to go. All you need, well, you can do it right in the editor, but otherwise you just need a text editor like VS Code, which is free. You can install it in 5 minutes. But you can also do it in the online editor if you want, and a browser. And that's it. It's all free, all open source. It helps, the canvas is a new HTML tag and system, a JavaScript system, but it was very low level and a little bit hard to do. Not very much help. So ZIM's come along and added many conveniences, components, and controls to make the canvas much easier, even easier than what Flash was. Flash was actually Adobe Animate, which is now Flash. It used to be Flash. Adobe Animate exports to CreateJS, which is what ZIM's built on. So we can use Adobe Animate with ZIM as well. There's the tutorials for that. That's called the ZIM shim. And there's coding basics right here. It's a great way to learn how to code. So all these are, there's intro videos about how to start, about coding in general, and it goes through all of these videos that you can learn to, or watch to learn how to code. Okay, so that's one. If you already know how to code, then there's the ZIM Basics, which is more specifically how to do things in ZIM, assuming that you already know JavaScript. You can see what we code in 5 minutes, but maybe a very quick way. We haven't even shown you really what can be made with ZIM. We've just talked about, well, we haven't shown you any specific examples. So under examples here are many examples of things that can be made with ZIM. Why don't we take a look at one? This is using physics right here, and it's not an interactive example, but what we're doing is we're taking a chain like that of jewels and puppeting it to this eye that is animating. So ZIM can animate very easily, and the physics can get linked up, and now we're connecting those two. So there's a sort of a visual example. Most of the things we're using are more interactive. So for instance, now we've got things that are following the mouse. Press. So there's that type of thing. We had mentioned work in 3D. Here is an example of that where we have a model, and when we press, there's a ZIM puzzle, and we can drag that around. You can make this puzzle. This puzzle is very easy to do because it uses the ZIM scrambler. You just say what image to load, chop it up, and there's a puzzle. And then we can put that puzzle onto a 3D model if we want. All right, so there are many examples here. There's also collections of different examples. So if you're interested in physics, for instance, ZIM has a physics collection somewhere in here. There it is right there. So here are a bunch of balls falling, and then there's beads. We're going to be doing something very similar to beads, and I wanted to show you beads. These beads bump into each other. But when we did our shredding, we don't want the pieces of paper to bump into each other. We want them to kind of go everywhere all crazy. So it's almost like this, but not quite. Okay. Anyway, there's collections for particle emitters, things to do with the motion controller, parallax, very many exciting collections of things. Those are like all mini sites. There's our interactive NFTs for making art. Here are a bunch of examples on CodePen. Some are simulations, so this would be a simulation right here where we're simulating fireflies in the forest. And that was a remake of somebody else who did it in HTML. And as it says in the code here, we're under half the size. So ZIM made this same thing in half the code that was done in HTML, CSS, and JavaScript. This is CodePen, so you can see all the code that gets used to make that. So any of these open up in CodePen, and there's lots and lots of examples. So these are the types of very colorful, very fun things that we can make. Okay, well, let's let's head back and actually do some code, shall we? So we've got the shredder, and this is the app. We're not really going to go over how the app was made, but more so how the shredded pieces came out of that. And we can use the ZIM editor as mentioned. So let's go up. Rah! And here's the editor right here. It would be on any of the pages. Okay, somebody was just asking about animating a point with a blob, so we quickly did that code here in the editor, and there she goes. But we'll clear the editor. You'll probably get it cleared. And the editor, you can log in as well. We're already logged in, and you don't have to log in, but if you log in, then you can save your files. And you can go, so here's our files. If we load them, we got lots and lots of files there to load. We can save files, and we do, and we provide these things called Zapps. So I've just hit on the Zapps tab there. And why don't we hide all of them? And you will see things called demos. So you'll see the feature demos, the basic demos, the mid demo. Okay, so lots of demos. Maybe more visually, though, it would be to take a look at it through the EXPO here. So if I hit EXPO, there's little thumbnails of them, or we could indeed launch the EXPO page and see, well, bigger thumbnails of them. So each of these allow you to, you can press them and go see how it was made to find out how we can animate along a path or whatever it may be. Okay, there's the coloring book. Ooh, how do we do that? So those are all demos, and they're in the Zapps, and you can make your own Zapps and store them if you indeed log in. It's also good for education. You can share these. You can share lists. They're called lists. So I have a bunch of lists of them, and I can share those lists with people. Anyway, we're going to make a new file. So here it is, test, and what I will do with this one is, let's make it a bit bigger so we can see the code. Well, too big, there we go. We will make a new circle dot center. You've heard of this one, huh? Center dot drag. There we go. And if I save that, there she be. So I hit Control S or hit test like that. And now there's our circle that we can drag. And there was mention of having a radius for 100, for instance, in red. And now we have a red circle that we're dragging. What we want to do is we want to shred a piece of paper that has some words on it. Luckily, ZIM has this thing called chop, which can chop up any, these are things are called display objects, so things that you can see on the stage, such as a circle. We can chop that up. Yay! We could also chop up a picture, and we can chop up a label. A label is some words, so that's kind of handy. Why don't we make a new label? New label. Oops, sorry for that. And we can say hello world, which is a common programming thing to see, and we can locate that label at 100, 100. That means it's 100 over from the top here and 100 down. Hello world. So we could chop that up into what's called a tile. You can also make a tile by saying new tile. And you can say what you want to tile. Let's see what the default is. And we'll center that. We won't bother dragging. And we'll comment out. This means a comment right there. You go Control / and it will comment it. So we've now made a default tile and centered the tile. And there she be. If we put the drag on the tile, it's kind of fun. If we put the drag on the tile, it actually will drag individually each thing unless we tell it some more information, all : true. Now it drags the whole tile. But anyway, we're going to use chop to make a tile. And our tile will automatically be rectangles. So in this case, it looks like it was a tile of circles, but we could say tile new rectangle here. And now that will tile, oh, and we're dragging all of them. Let's not drag all of them. We don't even really want to drag them. But anyway, there's a tile of rectangles. And you can also say how many you want. So say 10 by 3. And so that's 10 columns, 3 rows. And then here's the spacing. Why don't we do 10 by 10? Oh, well, maybe we did too many there to fit. We could deal with that. So there is an example of a tile. Are you guessing how we're going to chop up our label then? One thing about our label is we have to care for it a little bit in that we don't want it to be too big. We always want it to fit sort of into the shredder. So luckily label has a way to do that automatically. If we give it a label width and a label height, then it will assume you want to fit the text, as much text as you can, within that dimension. And so if you have a lot of text, it will make it smaller, and if you have less text, it'll make it bigger. So that works out perfectly for the chop. And we chop that up. We want a background color on our label, so it looks like a piece of paper. So yeah, there's some stuff there. I'm not really so interested in doing the label part, or even the chop part, but more so, how did we make it look like pieces of paper were shredding and moving? We can animate the tile quite easily by, there's a couple of ways, but instead of dragging, we can say .animate. And if we animate, we could give it a property, so say the Y value. We could give it a specific Y value. Here is the height of the screen. So you see this light area, that's called the stage, and it has a stage height. And we can adjust the stage height here by choosing that. Oh, well, darn, I gave away the animation already. That was portrait. Here is square. Here is landscape. And you can actually give it other specific dimensions as well, but these are the three basic ones. You can also make it more narrow, like it looks like the phone. So there's almost what our shredder would look like in the end, is a sort of a long, skinny thing and falling. So you see what we've done there? We animated the whole tile to a Y position of the height. So that's all the way down to here. If we animated it to 0, then it would animate the tile up to the top. And now we can see that the tile animates up to the top. You can also give it a time. That happens to be, these things are called parameters. That happens to be the next parameter. So if I said 5 seconds, this would take longer to animate to the top. And it also slows down. It starts off slow and speeds up. There's other ones you can do as well. The next parameter happens to be called the ease. And if we bounce out, and here's what happens. Boing, 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 boing. That's a pretty slow bounce. Why don't we speed that up, say 2 seconds. Boing, 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 boing. Okay, so that's the ZIM Animate. You can see that that's pretty easy, huh? But we want a little bit more than that. We want the pieces to kind of look like they're connected, first of all. They were more like long strips. So let's build some long strips. With our tile here, we said 5 by 3, but our rectangle, let's give this a, okay, well imagine that it's being shredded downwards for now. So that means we'll go back to the height, but it's not quite the height because we've got the height of, if we go to the H, its top left corner goes all the way to the bottom. One way to stop that is we can change the registration point of the tile so that it's, well, at the left is fine, I suppose, but at the bottom, ooh, okay, so that's bottom, oops, 2 T's, oh, and there we go. And now it does its registration points at the bottom, so now the bottom of the tile will go to the bottom of the page. And let's increase the time a bit on that. Ready? Boing, boing, boing. So it's almost like being shredded, but actually we wouldn't bounce out. We would probably want it to go linear. So here's what linear looks like. Linear. Oh, that's not right. Linear. There we go. Now it just goes at a constant rate towards the bottom and stops. But it took too long, so we'll go 1 second. All right, that almost now looks like shredded paper, but we wanted our rectangle to be long, thin things. So we'll do them something like 30 pixels wide, and how about 200 pixels long? Okay, we've got black paper, which looks a little bit awkward. So here in our editor, normally when we work with ZIM, we have a code template. Let me just show you that. So here's ZIM. Under code, this is where we would normally start. Right here is our template, and you hit copy, and that copies the template. The template has a framework like this. So that's us bringing in ZIM, right there, importing ZIM. And then we have a framework, and this framework says how big and what colors to use. So normally if we want to set the color of the stage, we can do it right here, and this is the outer color. And then here's where we start typing. So this is what's available in the editor. This is the function that runs when we're all ready to go. Okay, so how do we fit it in the window? Its size, the colors, and when we're ready, what do we call? We call this code right here. So this is what we're doing in the editor. All this stuff comes with the editor, so we don't have to think about it. So it's a little bit awkward because how do we set the frame color? And the way we can do that is we can say F for the frame, right here, F. F is the frame, the stage, the width, and the height. Those are all given to us. F.color equals black. So now we have it black there. That means we better change the color of the rectangle to how about white. Black is not a color. Did you guys all see that? So that's us saying, ooh, there's an error on line 4 here. So we want black. And there we go. So now we have some paper. In theory, although we could fix up that paper a little bit. I don't mind having little cracks vertically, but I'd rather not have those little cracks horizontally. So that's, here is the spacing horizontally. So that's okay. But this is the crack vertically, which is the spacing vertical. All right, so if we say 0, then it looks like now strips of paper. Cool, huh? So there's strips of paper. We can decrease that a little bit by, like, say 5, and we can make more of these things too. Instead of just 5, we can say, hey, there's 20 of them. And it's not too bad, but let's go with 15. Oh, not 150. We just did it. There we go. That's kind of what I was expecting. And why don't we go with 4? Do you think so? Let's go 4 of them. So we now have paper that is falling, but that's as far as we get. We have no, it doesn't look like they're twisting around or separating or anything like that. So in other words, not the best. And by the way, if we did want it to look totally like a piece of paper, it'd be more like that. We're still seeing little cracks there. That's just artifacts in this. This is scaled quite down. If we scaled it up, we might not see them, but you can do something like -2, and I think that will get rid of those things. So this is the spacing. If we say -2, then we don't see all those little cracks, and it looks like a piece of paper, and we could have had words on it. But that piece of paper isn't splitting up into all of its parts. Okay? So, in other words, we have to do something different than that. But I did want to just show you that that's pretty easy to do, isn't it? All right, and we could have chopped up the label. The label is simply chop. We pass in the label and say 15 by 4, and that will chop that up into a tile with the words on it. So I'm not going to bother with that right now. Well, I suppose we could. We're already sitting at a half an hour. Usually these explores go about an hour, and we have a little bit to explain when it comes to the physics that's coming up. One of the issues is, and by the way, if you want, you're welcome to go get a cookie, get a glass of water, relax a little bit, have some fun, come back to us though. And we'll go through that. Does that sound good? Sounds good to me, actually. But anyway, I'll keep on going here. I'm used to this. I'm a teacher, so we can. And also, when we're teaching, we usually provide little tasks to do. The students know the code somewhat. We teach them the basics, but then we give them little tasks. We let them try out to change these little things, and so that breaks it up as well. At a college level, we always want to make sure that there's activities, that the students are doing something. Okay, but anyway, you're just watching me do it, so that's a little different. Take a deep sigh, and or deep breath. Take a deep sigh. Deep breath first, then a sigh. And let's get to it here. So we want to put these things into the physics world. Let's do that. And what I'm going to do is select all that for now. Well, not quite all of it. Select most of it there. Comment it out and show you the physics world. Physics needs the physics. So right here, we turn on physics now. And what that would be doing back in your code here is, I don't think I can type there. No, I can't. We would just say import ZIM underscore physics. And then we would have physics. So that brings in both ZIM and this thing called Box2D, which was used to make Angry Birds, for instance. It's a physics library. And also brings in the ZIM Physics helper module, which gives us more code that relates to physics. We've also got those are different libraries. We've got a games library that brings in more things relating to games. We've got a 3D, a 3 library for 3D, etc. Sockets for multi-user. But anyway, we want physics, and to do that here, we click on the physics. And what that means is we can say, hey, give us a new circle. Remember the circle? We won't make it black, though, so we better make it some other color. Red is fine. Dot center. Oopsies. Center. And then, you ready? Dot addPhysics. I can do it. And now the ball falls to the ground. It's not very bouncy, but we can increase the bounciness. Bounciness, colon 0.8. That's a number basically from 0 to 1. And now the ball is bouncier. If we want to throw it around, we usually say, hey, we're going to be using physics. So what this did is if we haven't had physics, it will say, oh, there's no physics yet. I will add it automatically. But then it's a little trickier to gain access to it. You would have to go const circle. It's a variable. You would store the circle in there, and then you could ask for circle.physics. So this is the physics object that was made when we added physics. And then we could say dot drag like that. And now there it is bouncing, but we can also drag that ball around. Anyway, rather than doing it kind of backwards like that, we usually say const physics equals a new physics object. And so we set up a physics object. And one nice thing about that is that we can specify the gravity as well as and the boundaries or the borders of our physics. So that gets us a physics, which means we don't need to do that anymore. We just tell physics to drag. We could even tack that right on here as well. I don't even have a separate statement. So this says, hey, make a new physics object and tell everything in there to be draggable. And indeed, that still drags the physics object. If we don't have, the first parameter here is gravity. So if we don't have gravity, here's what that looks like. We're saying 0 gravity. The ball doesn't fall, but now we can bounce it around, and it's like air hockey. Can you see why we now like to teach this to kids? I mean, that's pretty easy stuff to get a nice, fun effect. We can bring other things in here and make goals and find out if these two things are contacting. But for us, what we want to do is add physics to each of those rectangles that we made in the tile so that we can apply forces to those. So let's just practice a force with a ball, and then we'll go and do the same thing with all those little pieces of paper. Okay, so instead of dragging, we have made our circle. Great. We have added physics to it. It's bouncy, but that doesn't really matter too much, I don't think. And now we can apply a force. There's a couple of ways to apply a force. One is to say circle dot impulse, like that. And if we say 10, that would be this is in the X or horizontally, and then the other one is vertically. So if we say 10, that's vertically. So if we say 0, oops. If we say 0 in the X and 10 vertically, that will be 10 going down. So if we save that, it just moved it a little bit. What about a force of 100? Boom! Okay, and there's a bounce. What about a force of 1,000? Boom! Okay, so that's how you can apply a one-time force, like hitting it with a cue for pool or something like that. Okay, we don't want an impulse though. Instead, we want to use force, which happens over time. It's much like gravity. If it happens over time, so if we put 100 here, hardly moved, just moved a little bit, but it didn't move as much as the 100 before. And you can see that with 1,000 as well. It didn't even bounce off the wall, it just made it to the wall. So force is a little bit different. It gets applied all the time, and therefore we need to do that in what we call a ticker. So we have a ticker dot add, and we can add a function. For instance, animate, like that. ZIM's got an animate, so we better not use that. Move. And what that will do is it will call the function. Here's our function, move. A function runs a block of code. So between these brackets right here that we just made, between these brackets will run constantly. And we better not make it 1,000. We'll make it 100. Okay, so now it's constantly moving. Oh, I should have kept the dragging because I can drag and it will move it back again. Okay, so now I can pick that up and let go, and it's constantly moving and bouncing. Let's make it move down. So a force of 0, 100, and down it goes. And I can pick it up and drop it again. It's just like gravity, isn't it? So that's what a force is. And that's what we're going to use to make our pieces move. We could have used gravity. It is just like gravity, but do you remember that our shredder right here is sideways? So it's like, yeah, darn. So instead of using gravity, which is a force, we're going to set the gravity to 0, as we did here. Setting the gravity to 0, and we're going to make the force move sideways. So for that, let's make it a landscape. So there it is now in landscape mode. And we will make our force go sideways. So that is indeed here. Okay, and now that's going to be our shredded pieces of paper going that way. Other things that we are doing with our force. Why have I got a bunch of these warnings? Moves, moves, moves. Unmatched bracket. Oh, because I haven't put anything here. Okay, there we go. So we just want a force going this way, and we're going to do it with our paper. So let's start building that out then. We'll bring back our tile here. And if our paper is the other way, then we want that to be 200 and this to be 30. So we're just, well, we could have rotated the top, but this is probably easier. 15 by 4, we'll make it 4 by 15. And that'll be fine, I think. And let's see if we still have our tile. Our tile's animating to the bottom. We don't want any animation to the bottom. We don't really want to center our tile either. We'll put our tile so it's over on the left-hand side. So the easiest way to do that, we do want to center it vertically. Eventually we want it to start off the screen. But for now, let's just put it so we can see it over on the left-hand side. And we can use pose for that. We can say 0, 0 from the left, center. So what that means is start off 0 from the left, that's over here, and start off 0 from the center, and that will look as follows. Test. Okay, so now our paper is over at the left. Why don't we make our paper a little bit shorter? How about we'll just do 3 of them here. And we'll get rid of this ball. We don't need the ball anymore. Let's see, the ball's being used here, so we will use a ticker eventually. I'll just comment out the ball there, and then we'll select all of this stuff right here and comment it out so we can think without having a ball bounce around. How does that sound? Yeah, is that good? How are you guys doing? Are you enjoying the Explore? Yeah, with Dr. Abstract and ZIM? That's good. Like I said, you're always welcome to go out and get a cookie, but I love this stuff. It's so much fun. So there we have our parts. Why don't we bring back our parts just a little bit so that we can see that they are indeed parts. And what we want to do is we want to make these parts have a force. Each one of them needs to have a force. One of the things with physics that's a little bit tricky is physics, the whole physics world has to start at 0, 0, which is up in the left-hand corner. This container of things, these objects are not at 0, 0. They're inside what is called a tile. So if I go dot outline right here, outline, we can see that there's a tile. Let's just move it in a bit so we can, a bit more, 50. Okay, so this is where 0, 0 is inside the tile right here. That's what that X is. This round thing is the registration point. By default, anything that's rectangular, like a tile, has its registration point at 0, 0 in the top left. So each of these objects have their own X and Y inside this container, which is the tile. We need them to start at 0, 0. So that's what I mean by it's a touch tricky. If we started off with our tile at 0, 0, that would have been fine then. So if we positioned it 0, well, in that case, we're not even positioning. We could position it 0, 0, left top, but we could just add 2 like that. That's with a dot. That's the easiest way to just add something at 0, 0. So now each of these objects, they're at 0, 0 within the tile, but they're also at 0, 0 on the stage. Okay? Which means the physics would work on them. However, if we put them in where we want instead of addTo, they're not 0, 0 on the stage. We can fix that, or they're not, their X and Y isn't relative to the stage, I should say. What we can do, though, is take them out of this tile container and add them to the stage in behind. So that's what we're going to do right now. We have made our tile. I won't bother outlining it. What we want to do is we want to loop through that tile. So give it a variable name. Const paper is equal to that tile. And then what we can do is say paper.loop. So each time we'll get a piece, maybe, and we'll call this function right here. So that's called an arrow function. Oh, I meant to tell you that I wanted to show you that we could have used an arrow function here too. That's what we would have normally used. This is what an arrow function looks like. Right now we have a named function. Function has a name, move. An arrow function is for lazy people, and programmers are lazy. Here's what an arrow function looks like. That's what it looks like right there. And it has a place that we can receive parameters. Then it has a block of code that will run. And we usually drop the block of code down like that. And then we would have put this right inside there like so, and not even bothered with the naming function. All right, so that's our lazy way of doing things. So yeah, we'll keep the lazy way there. Up here, we're using the lazy way to say loop through the paper each time we're given a piece of the paper. And then we can do things to that piece of paper. Piece dot rot for rotation, a random minus 20 to 20. So what this will do is it will randomly rotate each piece. Shall we try? There they are, randomly rotated. We could give them a we don't want to rotate, but we could give them a random alpha. Alpha is how transparent it is. So rand, just rand. That's between 0 and 1 by default. So now all of those have a random between 0 and 1. There's other ways to do that too. We could have done that as we tiled it, but this is, we want to operate after we made the tile. And what we're going to do, though, is actually put the things from the tile onto the stage. And if we do that, then the physics will work properly on them. Okay, so to do that, we basically say piece dot add to stage, capital S. S is our stage. So if we specifically want to add it to the stage, there we go. This is also tricky, though. We'll run into a problem in that if we're looping through a container of objects, and as we're looping, we're removing the object from the container, then that messes up the loop numbers, in a sense, or access. As soon as you take something out of a container, it's the container kind of, well, not shrinks, how to say it. The container no longer has it. So all those index numbers of everything else, like the third thing now is the second thing. So anyway, there's a solution to that, and that's to loop backwards. So we know that because we've been doing interactive media for a long time. So our next parameter of a loop is, hey, loop backwards, please. So now, there we go. We just put all of those things on the stage. They're no longer in the paper. If we didn't loop backwards, we would have had a really tricky error. It's one of the more tricky ones where it doesn't know how can I add it to. It's because what I was trying to do is add a piece that is no longer there to the stage because anyway, so that's a tricky error. Sorry for that, but it's not a ZIM thing. It's a general loop thing issue. Okay. Alrighty, now they're all there, we can add physics to them. So let's do that. We may as well add physics to them right as we're in here. So we're going to add them to the stage, and we're also going to add physics to it. Like that. When we do all of those pieces, do we have the drag on the physics still? Oh yeah, let's see. We added the physics before. Okay, right. We'll want to do this after we've made our physics object. What happened here is each one of these adds, well, the first one adds to it says there is no physics, and it makes a physics and adds that. From then on, each piece already has a physics, but then we made another physics. And so the drag is on a second physics, not on the original physics. So we want to make sure that we loop after we've made our physics. And now we should be, now you see how they're not falling because the physics has this physics is 0 gravity, whereas the physics previously had a gravity. There's also something else that's a little wrong. They seem to be bumping into each other before, and they're also going off the boundary. Like boundary usually is the whole stage here. The reason for that is anything that receives physics needs to have its registration point in the center. Rectangles by default have their registration point at the top left. That can easily be fixed by adding the proper registration. So reg center, like that. Now they all stayed properly, and now they're all hitting each other properly and moving about. So anything that goes into the physics simulation needs to have a center registration point. Okay, and we've just done that for each of our rectangles here. So now, that's good. We're coming along here. We don't really want to drag these rectangles. We just want them to push along with a force. So we're going to have to add a force to each one of these. When we do that, we have to constantly apply the force. And it helps. You see here how we looped through all of the paper pieces? Well, now those pieces are no longer in the paper container because we added them to the stage. We could at this point loop through all the things on the stage, which currently is just all the O, but that also includes the original paper container. So even though we've taken everything out of the paper container itself is still on the stage. It's empty, it has nothing in it. But anyway, and there might be other things on the stage, like we had a bunch of interface. Remember all this stuff? All this is on the stage as well. So we don't want to just loop through the stage. Luckily, there is a fairly easy way. When we make a tile, such as paper, remember paper is our tile right here, we have an array of all of the items as well. And that's called items. So we can ask the tile right here. We can say tile, oh no, it was called paper dot items. That gets us an array. And we can loop through those. So here we go, loop, paper items, and each time we get an item is fine. What did we use before? What name did we use? Do you remember? We used piece for the piece of paper, but whatever, it doesn't matter. Okay, there's our arrow function. And each time we loop through an item in the array, so even though we move them out of the container itself, it's still kept in the array of items. So that was lucky. Otherwise, there's other ways that we could have dealt with that. We could have made an empty container at 0, 0 and added them to that empty container at 0, 0. The physics would still work, and yet we would have all our pieces in a container again, and we could have looped through the container. But anyway, this is fine. So that gives us each item, and what we want to do with the item is dot force. We want to force it a little bit, 100 for instance. So now what we're doing is every time, like this is 60 frames per second. So 60 times a second, we're adding a little force to the item in our, and there they all go. So we're getting there. I'll test again. There they all go. One thing that is different about this one is you see how they're all hitting each other? They're all hitting each other, and we wanted them not to hit each other. So that's a tricky thing as well. There happens to be in physics this thing called maskBits and categoryBits. And this was inherited from Box2D. So Box2D is the physics engine that we're working. And our physics module, our ZIM helper module that does physics, this little check right here, brings in Box2D. It also brings in our physics module. Our physics module makes physics 10 times easier. If you tried to work with Box2D, you'll have 10 times, seriously, 10 times as much code. It's just so separated. Engineers made it, and there's just like, you can divide up everything into all of these parts, and we just made it easy. This part.addPhysics, and that does 5 lines of code. So anyway, we inherited this maskBit and categoryBit and decided that it'd probably be best. We don't use it a lot. I would say that in 95% of the things that I make with physics, maybe even 99% of the things that we make, I want them to bump into each other. But sometimes you don't want the physics things to bump into one another, and that's when you use these maskBits and categoryBits. So that can go right in here. We can say maskBit :2. And if we do that, what that, no, it didn't work. maskBits, plural. There we go. What that just did is now they don't bump into each other, but now they don't bump into our walls. Okay, right, check that out. Let's try it again. Test. There they all go. They don't bump into each other, but they don't bump into our walls. It's like, rats. So we may as well not have the walls. And this, if we put in none here, N-O-N-E, like that. By the way, that's a ZIM constant, much like center and left. You can also use quote center, lowercase, and that will be the same thing. Anyway, we now no longer have walls, so let's just check that out. We have no walls. I'm going to take away the maskBits. Remember what happened when we had walls? And I run it. There we go. So no walls, and off it goes. If we didn't put none, just making sure that you understand here. Here we go. Oh, wait a minute. Oh, the maskBit somehow got back. I don't know how. Okay, so there we go. All right, there's a wall. Let's go none. Remake, sorry, F11 by accident. F11, by the way, does full screen on your code. N-O-N-E, no walls. And now we're going to take the maskBits and the categoryBits. Well, you know what? Let's bring back the wall then. So we want to make a wall. We actually want to make 3 walls. We're going to bring in our physics objects from the left-hand side. So we want them to be able to go off the stage, which means we don't want a wall on this side. But as they hit the bottom, we want them to be able to hit the side walls as well, like it's inside a container. So we really need a wall at the top, a wall at the bottom, and a wall at this side. For now, let's make a wall at the bottom, and we can show you what that's like. New rectangle. And we want this to be, if it's at the bottom, we'll make it, I don't know, 50 wide for now. And we'll make it the height of the stage. So this is the height of the stage. Also give it a color so that we can see it red. We'll make a red wall. And we will pose it. Remember our posing? This time we'll pose it 0 because we'll center it. Or we can, 0 from the right-hand side. We can center it or top it. Doesn't really matter. And then this is from the right, and this would be from the center. And there's our wall, except it's not in the physics yet. Let's make it a little bit shorter, minus 100. Okay, so now our wall is a little bit shorter, And instead of going right at 0, let's go 50. So you see that? We've positioned a wall that's a little bit shorter in height, 50 pixels from the right and 0 from the center. If we use at top there, which is default, so we don't need it, then it's 0 from the top. If we said bottom, oh, I spelled bottom right, good, then it's 0 from the bottom. But if we say center, then that's 0 from the center. Okay, what our wall is missing though is physics. So we need to give it physics. Dot add physics. And do you know what's going to happen to that wall? It just got wiped out. All right, I forgot there was no gravity. I thought it was going to fall. So if our gravity were 10, then it falls. So that wall falls. All the other things fall as well. Anyway, we'll go back to a gravity of 0. Why don't we make the force a little bit less too? Why don't we make a force of 10 for now, and it'll head slower to that wall. Oh, did you see what happened? I'm glad we did that. It didn't hit the wall at the right place. Do you remember why it's not hitting that wall at the right place? Because we didn't center reg our rectangle. So dot reg in the center of our rectangle. Now it will hit the wall at the right place, and it pushes it away. We can stop it from pushing away by saying false here. The very first parameter of addPhysics is it dynamic or not? Can it move? So here we've made false wall. Now it won't move. Excellent. So now all these pieces are stuck pushing against that wall. They're staying nicely because the physics is like being pushed kind of exactly. That was one thing that we had to fix up or change with the physics of our paper, is we had to cheat a little bit and give it some side forces and give it some rotational forces so that it actually curled and moved. Otherwise, all these pieces of paper would push, and the physics world was rather exact on it. They would just be sort of standing right on top of each other, as we see there. One thing I wanted to do, though, is make sure that right now these things all hit one another still. You see that? And we're wanting to make those not hit one another, yet still hit the wall. So the way that's done is, here's all of our pieces. We set the maskBits to 2. Bits go 0 to, how does it go? 0, 2, 4, 8, 16, 32, 56, 128, 256. You probably recognize those numbers. Yeah, those are powers of 2. So you can set any power of 2 you want here, but it does need to be a power of 2. And by default, 0, everything's at 0, so everything normally hits one another. But as soon as we go maskBits 2, that will only hit objects that have a category bit of 2. Okay, so if we say maskBits 2, now these things don't hit one another, but they don't hit the wall. So how do we make it so that they hit the wall? They don't hit each other, but they don't hit the wall. Well, you would say the wall gets a category bits of 2. So we already have one parameter here. Category bits is, we'd have to go null, null. We'd have to go find out which parameter is the category bits. And unfortunately, that's like way down here. By the way, you would look under docs, addPhysics. Here they are, dynamic. How much do you want to contract? That can be handy if you want to have a wheel go on top of something, then you can contract it and then the physics hit inside, sort of thing. The shape, that's handy if you bring in a picture of a soccer ball, for instance. That's a rectangle. The pictures are a rectangle. So if you say shape circle, it will take that rectangle and treat it as if it's a circle. And you can make the picture of the friction, linear, damping is how quick. Anyway, you've got lots of things here. And here is the maskBits and the category bits. So what we're going to do is we're going to switch to how we did it here. And that's called the ZIM DUO technique. That's one of our features where we can use the squiggly brackets and use the name of the parameter and a value rather than just the parameter and the order. So we could do the same thing here with the rectangle. We could have turned these all into squigglies and say this is the width is 50, the height is that, and then red, is the color. Sorry, color is that. And we could just jump right to the fact that it's got a corner, colon 20. And now it has a corner. Okay, and we don't care about the order. The order of these things no longer matter. We can skip a whole bunch of parameters. Otherwise, we would have had to do those parameters in order. And that is one of the a great advantage to ZIM. It actually can be done in a slightly different way in Python. We didn't know that, so for 8 years we were thinking, yeah, that's our invention. And it turned out Python does it too. So anyway, that makes Python easier as well. So we need to do that here with the addPhysics. Instead of saying false, we would say that this is dynamic colon false. Then we don't need to worry about all these parameters. We can just jump directly to categoryBits. So it would be the same as in our docs here, right there, categoryBits colon 2. So if we set the wall's category bits to the same thing as the piece's mask bits, then they'll hit. We've got an error somewhere. Category. Oh, we forgot the last bracket there. There's the last squiggly. And here they go. Oh, and they did hit. I thought they didn't hit because it looked like they were going through, but now I realize what's going on. They just all clumped up onto each other. Okay, so they're not hitting each other, but they are indeed hitting that wall. However, they can slip by the wall there. Oh, there it goes. All right. So that's why we want the walls to be on the top and the bottom as well. Hope you're doing well. We've hit an hour now, but we're almost there. I just want to continue on with the simulation by making it sort of float normally across, but then at some point it sort of breaks up and curls. One thing we want to do though is turn these into joints, so we better do that right now. That's maybe the first thing. So we can join things together. Remember the love beads that we showed, those are joined together. We can join the parts of our paper together. It's a little bit tricky. Can we do it here? Let's do it before. Okay, we've added the physics there. Well, we're adding it to the stage. Okay, we can just loop through the items. That'll be fine. So paper dot. Loop. When we loop, you might have wondered, paper.loop versus loop paper. All right, that's an important distinction. Paper is a ZIM object, and it has a loop method. So paper is the ZIM tile. Loop or paper.items is an array. That's a JavaScript array. The JavaScript array does not have a loop method. So therefore, we're using the ZIM loop function. So this is a ZIM loop function that can loop through an array. And we're going to have to, and we'll use that again. So here we're going to loop through a slightly different array. Instead of the items, we're going to loop through items 2D. Items 2D, I believe that's it. And each time that will loop through each of the rows and give us an array of columns. Okay, so if you want all of the items, then that's items. But remember that if we test this, we want to join these three, like each column in a row. We want to join those together, and so we're going to loop through each row, and that gives us a row. Oops. So there's our row. We use the arrow function this way. There we go. We use the arrow function to get that row, and now we want to join those three parts together. All right. to do that, we use physics.join, physics.join. The problem is we need two of them to join. So on the very first row, if we want to know what's the first row, we can collect which row number we're on. So this gives us the row number. This gives us the parts in the column. So here, why don't we apply no physics just at the moment. And I can describe this a little bit better. So this is a row, and that's another row, and that's another row. This is the first thing. So the very first time we loop, we get this. We get this one, and this one. So we get an array of this, this, and this. This is the 0, 1, and 2. If I, that's I, our iterator, we call it. I don't have to use I, we could use j, etc. But anyway, I will be 0 for this one, 1 for that one, and 2 for that one. We want to join these two together. So if we only have one of them, we don't really want to do anything yet. So what we're going to do is skip our loop right here. So right here, if I is equal to 0, remember use double equals for a comparison, not an assignment. That would assign 0 to I. Now I would be 0. But this compares it. It finds out, is I 0? And if it is, we return. What return does is it leaves this function because we don't want to do anything if we're only on the first one. Okay. Now we want to join the current one, the current row, well, the current column, I guess maybe I should call that, yeah, so this would be, yeah, this is for the first row. Oh, this is for the first row. We have to loop through the row. Okay, so now we loop through the row, and each time we get an item. And it's actually here that we care about the 0. My apologies. So this is I now. We don't really care about the I on here. It's funny, not our fault, but this is a nice thing from JavaScript. For this guy, the arrow function, if you only have one parameter that you're collecting, you don't need to put the round brackets. You can just leave the round brackets on. So we're quite used to doing that. Isn't that weird? But if you have two parameters, then you got to bring back the round brackets. And if you have no parameters, you have to use the round brackets. So it's a little bit awkward to teach that. Anyway, we need the squiggly brackets in here. And then this stuff goes in those squiggly brackets. At this point, you're going, coding? I'll never code. This is way too complicated. My apologies. So we're looping through each row. And each time we loop through the row, we're going to take that row and loop through to get each item. This item, this item, and this item. And those are the three things we're joining. Then we go to the next row, and we join those three. We go to the next row, and we join those three. So that each one of these is in a long strip. See how that works? All right, so if I is double equal to 0, and this thing's wanting me to compare to 0.0, but don't worry about that. If we're on the first item, then don't join yet. If we want to join now, the way we would join is item. So great, we would join an item to the last item. But we don't have a last item unless we specify it. So inside here, if I is 0, return, else we want a last item. So no, even if it's 0, we want a last item. So this is not quite right. By the way, if you only have one thing in your conditional, you can put it onto the same line. But as soon as you have more things in your conditional, for instance, we want to store a last item. So let last item. We don't know what it is yet, but we're going to be ready so that as we loop here, we'll always remember a last item. Last item is equal to item. Okay, so if it's 0, all we really need to do is remember the last item. Then we join, doesn't really matter, the last item to the item. Okay, that will join these two things together. There's a few different ways to join things. You can weld things. So by default, this will weld them. We're going to take a look at the welded version. But then there's other ones. There's a revolute, which is it revolves. That's what we'll end up wanting to use. There's also a distance one, which will just keep the distance between 2 points. And that can be handy sometimes, but that's not what we want in this case. But for now, we'll do the default weld right now. And we're missing something. Do you see? So coding is like a puzzle. Do you see what we're missing? We have a last item the first time, and then we're joining the last item when when we're on the next column. I will be 1. So this was when it's 0. When it's 1, we have that item, and we're joining it to the last item. But when it goes to 2, the last item is still going to be the first item, which actually works when you weld it, because we would weld this item to our first one too. And then they would all be welded together. Let's just see that work. So now all of those are welded. But this last one is actually welded to the first one. You can almost tell. This seems to be welded stronger, and this one's like a farther kind of weld there. Interesting, huh? Okay, what we really want to do, though, is make sure that the second one gets welded to the first, and the third one gets welded to the second. So we don't have that in place yet. Can you imagine what you would need to do? We need to, after we do the welding, we have to make a new last item. Last item is equal to item. There we go. So now all of them will have their items, and it still looks like it's welded, but it's actually welded stronger. I can see there's no movement there. Anyway, we don't want welding. Let's see what that does once we add the force. It probably will still, they'll stick exactly on there, because as you push, there's no sideways pushing. So let's see what happens when we bring back in the force here. There they go. Yep, still sticks. But now we got longer sticks. Like bamboo. Okay, so we'll take off the force while we're working on this still. And now what we want is a revolute joint. So that's a different type of join. And we say, where do we want to join that? And where do we want it to revolve around? Basically, we want it to revolve around the end of, between these, the end of the last item or the beginning of the item. So it doesn't really matter. Item dot x. So that will be the x position of the item, which is good. That's the beginning of the item. And then, oh no, wait a minute. The x is in the center. So because we've centered regged, there it is right in the center. So we have to subtract half the width of the item. So minus item dot width divided by 2. So that's the x position where we want to rotate about. And then the y position is we want to rotate around half the height of the item. Oh, which is the y position. So that's good because the y is in the middle. Right? X and Y are both in the middle of the item. We want to rotate around the middle, but over here. So that would be item dot Y. Oh, that gives us, that's 2 items. We have X and Y's, but now we have to say some other things here under the docs. Let's have a look. This is under physics. Physics. Go. Physics. So under physics is the join method. Remember here we have the physics and we're using the join method. So I look for physics, which is this object right here, physics, and I look for what methods. What can the physics do? When it joins, how does it do that? So there's a lot of things going on in physics because we talked both about Box 2D and ZIM. So we have to be a little bit careful. There's all the parameters for physics, including gravity and the borders. Here are the methods. So we want join. Object 1, object 2, point 1, point 2, minimum angle, maximum angle, and the type. So point 2, right, I see what we've done wrong. These are points, point 1 and point 2. Point 2, it says here, is only needed for the distance joint. Okay, So we don't need a point to. What we do need, though, is to put this into a new point. So this is the x of our point, and this is the y of our point. The second point is null. We don't need it. That's only for distance. Then we have min angle and max angle, which we actually will want to do. Let's do a min angle of 20 and a max, a min angle of 20 and a max angle of, I don't know, 90. That's how much these can rotate around one another. And, oh, but min was, should be negative. Negative. We'll go negative 90. How about we'll keep them at 45. 45 and 45. Anytime you're doing a simulation like this, these are configuration parameters that make your simulation run a little bit differently. We could have these fold right on top of one another. We could have them hardly fold at all, etc. But anyway, we can also randomize it. Maybe we don't want them always to be the same. It might look better if they were randomly done, which is how we did it in our shredder. And then finally, what type is it? So the default is weld. Then we have distance, and we have revolute. And it is the revolute that we want right here. That's a fancy word for it revolves, I guess. All right, so we run it now, and oh, look at that. So we're getting 45-degree angles. It's pretty bouncy. These guys are pretty bouncy. We probably don't need these things to be as bouncy anymore, do we? Where did we do that? There's our piece. Oh, maybe it's just default bounciness. Oh, I thought it looked... Oh, I forgot we don't have walls at the side. Okay, anyway, maybe it's just springy. Prang, prang. Yeah, it's a little springy. Okay, but not bad. They're starting to look a touch like a piece of paper, aren't they? And then they would get pushed and curl. They probably still don't curl. We're almost there. And why don't we... some of these other things are nuances. I don't want to go too much longer than an hour and a half. So why don't we just add the little bit of extra forces to this to make it actually feel like it's curling up. We do have a couple walls to make, and we want to put this wall off the screen, but for now we'll leave it where it is, and let's just do the force to make it kind of curl, or at least get mixed up. Because right now, if we bring back the force, it probably still is too directly on to cause it to move anywhere. So we want these to move a little bit so they start doing that kind of stuff. All right, the way we do that is we can apply a side force, or we can make it, the side force, as these are falling, I don't really expect too much side force to happen to them. So we didn't apply a side force, but we did make them fall at slightly different speeds. That was one thing we did. And that meant that as they were falling, it's still readable, but they started to split up a little bit. As a matter of fact, it'd probably be a good time to come back here and add another stress. So I'm going to refresh here, and let's add another stress. We need to know what the code is. Oh, we have to wait. 977, but it's just about to change. 794. 794. 794. Isn't that nice? This is a ZIM component that allows you to pick that up and drag it faster or slower. But we better get there for next. That's called the picker. And it can work with numbers, but it can also work with strings. And that's one of the ZIM components. These are tabs right here. So this is another one. Will this wind? How about we just put wind? Okay, so there's a nice thing, and this will be personal. Oh, I'm stressed out about the wind. And I'm going to confirm, and I have 16 seconds to look back over here. So now we're going to get this piece of paper that has this big wind on it, and we're going to watch carefully as it animates across. It will sort of keep its side animation, but split up a little bit. That's because we made it have different forces. And then, after a little while, so here we come, and watch the ends here. There they go. And then it starts to curl. So it splits up a little bit because we're pushing at a different rate, force. And then it starts to curl. And the way we did the curls is we come back here. We applied rotational force. And there's a spin. A spin will do a one-time force. Probably could have just done that. But there's also a rotational force. And so if we add the rotational force in here, item.torque, that's called, and we can torque a certain amount. If we torque 10, then they're all going to get torqued to the right. And there they go. They're all kind of being torqued equally. So it would make sense to torque a random amount from -10 to 10. And we need another bracket there. So now they're all getting torqued in a random way. Not bad, huh? And it starts falling apart. And if we put the walls on the side, that would be as well. To get the random forces in, if we did that right now, rand, say 8 to 12 or something like that, 8, 12, then they would go at different speeds. Actually, let's take off the torque so we can see those different speeds a bit better. Okay, we might need more. 15, 5 to 15. Okay, see how they now are starting to split up at different speeds. We bring in the torque. And there they all go, and then they get bent. In our example, I think we allowed for more bending. And actually, we applied randomness here as well. So we did something like rand minus 90 to minus 40. And here the rand 90 to 40. Oh, well, it's supposed to go the smallest number to the biggest number. That would have worked, but keep it like that. So now each one will rotate more or less than some of the other ones. That one's kind of stuck in straight. We might have increased the force to push them faster. We had to watch it. So in ours, we wanted them to be able to read it, but we also wanted it to look like falling paper. So we start off a little bit slower to give them a chance to read it. We then shift the forces on them, and then we increase the force at a later date. But for now, we'll just increase the force here. We'll make it 10 to 25 or something. So there they go fast, and they're falling, and they bump. Okay, and all that would have been kept in place if we had more walls. Here's how we move a wall, for instance. We're nearly there, huh? Where'd those walls go? There's the physics. There's the rectangle, which is a wall. We'll make it the height. And instead of positioning it 50, we'll position it minus 50. And now it's hidden. So it's, instead of 50 from here, it's minus 50. So it's hidden. Actually, if it's in half, I think that's good. Yeah, they're all just lying there on the ground. We get some sidewalls on there. Let's make some sidewalls. Just take a moment. This one would be the width. And if we want 50, it's red, center edge, so the physics works on it properly. And it would be positioned minus 50. This is above, so that would be up from, and 0 from the center, and top, which is default, so we don't really need it, but there it is, and we do need that bracket. So that would get us a top wall. Now there's a top wall there, and then the bottom wall will be quite similar. Same size, except center at the bottom. And now we've got a bottom wall as well. we got paper to throw around. And we didn't want to throw around the paper, which means we comment out the drag here. And now we can't throw the paper around. And we've got our shred. Isn't that wonderful? So the last thing is just shredding the word. So instead of having the tile like that, we would make a, I think we made, well, I should be able to do it this way, const. Now we already have paper. Well, okay, we may as well use paper again. That's supposed to be the tile eventually. I want it to be a container, so we'll call it holder for now. Equals a new rectangle. And we can make this be something like, this is the width of the rectangle, 200, make it 300 by 100, 200. It will be white. We will then say new label, and the text of the label will be hello world. It can be black. Oh, that's as a string though, so put quotes around it. It can be black by default. It is black by default, so that's good. We'll set the label width. Did I spell that right? Width. Label width of. We want to rotate this, so the label width would be 200, and the label height. You don't usually have to do this, but this would make sure that our text scales to the size. Well, for this, we could just, without wrapping, like if you're going to have text that will wrap, then you use label width and label height. For our purposes, let's just keep this simple. But you're welcome to look at the code, the actual code. Label width and label height would allow you to put any text into a certain box, but we don't need to do that. We can just say dot scale to. Let's swap this up so it's, well, if it's chopped, it's going to be rotated. The thing is, it's rotated, and scaling it to, I don't know what happens if we rotate this and then scale to dot rotate. I can do it. Rotate -90 and scale it to the holder, something like 80%, 80%. And let's put that on the stage and see if we see it. So holder dot center for now. So there it is, but I don't see the, oh, I didn't actually add it. I've rotated it, I've scaled it, but we didn't dot center it on the holder. Oops, spelled right. Holder. Okay, so there's hello world. Rotated and scaled onto the holder. It might be more, it might look better if we put a new line in there. Where'd it go? Where's our text? There's the holder. I accidentally deleted the text, I guess, when I saved it. Okay, center on the holder. If we put a new line in here, \n, it looks like that. It's not centered, so I can quickly set some style here. ZIM's got style, align, center, and apply that only once, :true. Now it's centered on there, and we're going to chop this up. It could be bigger, couldn't it? So how about 600 by 300? That looks nice. Hello world. What else do we want with this? There it is centered. Now we want to chop it. So I won't center the holder. Instead, I'll chop the holder. And indeed, that will become our paper. Const paper is equal to chop. That's a ZIM method. The holder. And what are the pieces for the holder? What do we have here? 3 by 15. I think we can use the same. 3 is columns, yep, and 15 is your rows. Good, and we will dot pose this in the same way. Well, actually, yeah, okay, we can pose it in the same way. We don't need this other one here. So there it is, chopped and .posed, and then this one will comment out. And there goes hello world. Oh, we didn't center reg the chop pieces. Okay, so when the paper got chopped, the parts are not center regged. So that's a little bit tricky, but we can loop through the paper, paper.loop, and grab each item and say item.reg center. That did it. Okay, and there's our message. So did you see that? Our message is actually on there. Hello world. It looks like, yeah, it's not quite working. I think our reg center. Oh, lost center for some reason. There it is. Now it's working. Okay, and there's all the chop pieces with the actual message on it. You can see that as it's going initially, it almost becomes unreadable quite quickly. That's why we didn't apply these other forces right here. So we only applied a single force. And it wasn't even a random force. It was they all had the same horizontal force until a timeout. And then once the timeout, so a timeout is, well, we wouldn't do it in the loop. Timeout, 1 second, run this function. And in that function, we changed these force values. So we had to set up a variable to do that. But after a certain amount of time, we changed what these are. We didn't even have any torque at the beginning. And that allowed it to all move together. And then we started making it move differently. Isn't that wonderful, though? All right, so that's the world of ZIM. I am Dr. Abstract. We were demonstrating the ZIM shredder here for Sheridan stress shredder, so that we could shred our stresses. And sorry, you can't try this for now, but maybe if we do provide a link at some point to the sort of standalone app, not the gallery app, then we'll put that link in the video and you can check that out. But if you're in the gallery, I hope you've enjoyed watching how the shredder was made. Possibly we'll consider it. The app itself also has a lot of interesting, exciting things to be able to make this stuff. We made this in a day, or like this was made in a day, the shredding was made in a day. So 2 days for this app is basically unheard of. This type of app usually takes a month for a team to make. So that's because ZIM is very easy to use. Also, I'm quite good at it, I suppose, so I made it. But eventually, you can get to a point where you can make these things. Almost all of the things in ZIM that are in those examples are made in a couple hours, where you can make lots of things really quickly. Anyway, there's the chop. Did you see the chop there? And here's some components. We're animating parts in. This is a button. It can have a rounded corner. There's all sorts of components, all sorts of things that can be made. Oh, we have to try again. That was called a pane. So maybe we'll do an explore of how this part was made. Plus, there's also the data. How did we get the data from the mobile device here to the shredder? There's the data involved in that. All that was coded back in here with PHP and could have been a Node.js app. We do ZIM with Node as well. Many of our tools are made with Node, but we have ZIM, a couple things built in ZIM that make that really easy as well. So there you go. I am Dr. Abstract. This has been a ZIM Explore. And I hope that you come in to ZIM, zimjs.com, and join us in the forum as well, which is at forum.zimjs.com if you have any questions about this. I teach it at Sheridan in interactive media. So if you're at Sheridan, check out interactive media. It's actually called Interactive Media Management. And I am Dr. Abstract. I'm also inventor Dan Zen. All right, have a great day or night. Cheers.